Hello and welcome to All to Do with the Blue. I'm your host, Rowan Weitz, and this is a show where we talk about everything and anything related to water. Tonight we'll be having on a guest who is working for their PhD in, oh my God, don't let me get this wrong, physics and astronomy. Both of those, Alex?
Just physics.
Oh, just physics. Okay. Sorry.
That's good.
That is Alex. They are studying for their PhD at the University of Minnesota. Welcome, Alex. Maybe give us a little information about yourself.
Yeah, so I am a grad student at the University of Minnesota, entering my sixth year there, so hopefully leaving soon. And I am studying an astro in the physics program. Currently studying gravitational waves, but I studied exoplanets when I was in undergrad.
That's awesome. And the gravitational waves thing, I remember we were talking about that is so cool. But we will be talking about something else tonight. We will be talking about water in space.
Yeah. I'm very excited to talk about this.
Heck yeah, me too. So water rarity in space. We were talking a little pre-show about habitable zones, etc. Can you give us a dive in on, your information, the things you've learned, the things you know about water in space?
Yeah. So, in terms of how rare water is in space, water is made up of hydrogen and oxygen. Hydrogen is the most abundant element in our universe, and oxygen is also pretty common. So, water is not rare. We can actually look at the chemical composition in our own galaxy and measure most common compounds, and water isn't the most common. Uh, Carbon monoxide actually holds that title, but water is pretty close.
So we're a special planet.
Yeah. And in the fact that we have as much water as we do. I mean, well, I think we're a special planet that we have life, but
True. Very true. Very true. We're lucky to be here, that's for sure.
yeah, we're also in something called the habitable zone. So uh, if you imagine a star similar to that of our sun, and you have like an object like a baseball or something, and you can slide it close to and far away from this star, and you move it close, it heats up naturally. Move it further away, it cools down. If you do the same thing with like a glass of water, you can find regions where water will be a gas close up to the star, solid far away, or a liquid as it's in the Goldilocks zone or the habitable zone. And this is where Earth happens to be. Uh, we also have Venus and Mars close by the habitable zone, depending on how you define it, sometimes in or out. This is where, water is a liquid at the surface temperature. We see with Earth, we have a atmosphere that's able to hold in a little more heat. So the surface temperature would actually be at, I think, negative 40-ish Fahrenheit. But we have this atmosphere, so now we're at like around 40-ish Fahrenheit positive. So Mars doesn't have an atmosphere, or it has a very weak atmosphere. And so it just has that surface temperature, which is much colder. And Mars has a runaway greenhouse effect in its very strong atmosphere. So its temperatures are way hotter, even though they're very close to this habitable zone.
Oh, Venus.
Yeah, Venus.
Yeah, because there are like big volcanoes and stuff. There are constant action over there. We would die in a
Yeah.
second.
Yeah, I think we've sent probes to Venus and they can't survive for very long. I'm trying to remember the longest that a probe has survived. I believe it was for only a few hours. Um, or maybe even a day, but it was a feat to even get it to touch down on the surface.
I think I was actually just reading an article about that not too long ago because I think it's, oh my God, I can't remember what country it was because I don't think it was the United States. I think it was like Russia or something
Yeah,
where
yeah,
they got like a couple pictures of the surface, like really bad pictures kind of aimed at the ground, but they still managed to get something.
yeah. That was a huge feat of human ingenuity to get that.
Let's see.
Uh,
So if we say that, Mars's atmosphere can't hold water because they have some ice caps, so there's no water. But Venus is a
mhm.
lot hotter, and if Venus is more volcanically active, is there if they're producing, you know, plumes of smoke and stuff, is there more of a chance that there is a high humidity point there or that there is water?
I believe the surface temperature of Venus with the like atmosphere that it has is is so hot that if there were water, it would all be like evaporated. There wouldn't
Oh,
be any liquid
interesting.
water.
Okay, okay.
And I don't remember the offhand the composition of Venus's atmosphere, but I don't believe that it has that we know of any water in the atmosphere. Um, because we've like we can look at Venus and measure the composition of it.
Yeah, so then it would really suck to go there. You and
Yeah.
your
Yeah.
Not for the people who love to get a tan, I guess. Maybe they could just burn their skin off.
Yeah.
Then if we went to Mars, the because I know does gravity? No, that doesn't make sense.
Gravity is lighter on Mars because Mars is smaller than Earth.
So would the water float away, or like if there was liquid water on Mars, or I guess that would change the atmosphere. Would that make the gravity
So
heavier?
so one of the reasons why Mars doesn't have as much of an atmosphere is because it's not as dense. It doesn't have the weight to hold an atmosphere as well. I believe it's one of the many reasons why. One of the other reasons is that Mars doesn't have a magnetic field as strong as Earth's, and so when there's different solar flares or solar storms that would hit Mars versus Earth, Earth is able to pretty well deflect it and have it go to the poles, and that's how we see the aurora. But Mars doesn't have that same uh, mechanism for deflection, and so it just scatters the atmosphere.
Okay, so let's say I watched a video not too long ago about what would happen if the world teleported all the water onto Mars from Earth right now. What do you
Mhm.
think? What do you think would happen? Would the water like float away at all?
No, I think the water would stay on. It would. I think it would freeze up
Oh, okay.
really fast.
Instantly? Okay, okay.
Yeah, I mean, well, I don't know. So because water is unique in that its solid parts float on top of the liquid parts, it kind of provides this buffer for the liquid parts. So it would probably take a little bit longer for it to freeze up if we put all of the Earth's water on. Um, but eventually, because Mars doesn't have any or doesn't have as strong of a internal heating system that Earth does, it would not last, the liquid, it being liquid.
Okay. Yeah, that makes sense. It just turned to ice slowly. Or well, I guess the top layer would turn really quick and then it would take a little while for the rest of it underneath.
Hmm. Hmm.
Oh, be
Yeah.
Mars's biggest ice skating rink.
Yeah.
Closed to the public because no one can get there.
Yeah.
All right, so we know that Venus is closer to the sun, so it's hotter. Mars is further away and it's colder. And Earth is in the perfect spot where we have our nice blue water. So, with planet distances, do star sizes matter as well?
Absolutely. Star sizes definitely matter. We expect that other stars that would be habitable for life are actually smaller than the sun. It has to do with some of the stability of the star for like how long it will exist. Our star is supposed to exist for 10 billion years. Smaller stars are supposed to exist for much longer in a like stable state. And the larger you go, the shorter period of time that it is in that stable state. But as you decrease the star size, you have to get much closer to be in that like Goldilocks zone. It does lead to some other issues. We talked a little bit about radiation and how that affects atmospheres. The closer you get into the star, the more radiation that you're going to experience. And so, any planet that would be able to have liquid water would also need to have a very strong magnetic field, which in some cases means really fast rotation of the planet itself.
Oh my God, there's a lot that goes into this then.
Yeah, yeah,
So, so it depends on the star size, the distance, how fast the planet spins. And this is just to get some frickin' water.
yeah.
And what about the size of the planet?
So the size of the planet, we expect um there's this category of like of planets that are called super Earths. It's just Earth but a little bit larger. And between slightly smaller than Earth size and about I believe it was like 3 to 5 times the size of Earth, we expect to be pretty habitable. Um, what that size usually means is it's a rocky planet that has a different metal composition, and has a possibility of water and atmosphere and all of that. It's a kind of sweet spot
You know
to
what I'm
get all
thinking
of the
about right now?
what?
Avatar.
Yeah.
Great movie, by the way. I think it's the
Oh,
second one. That's the water one or whatever.
yeah, yeah, Way of Water.
Yeah, really good too. Uh,
Yeah.
that's all I can think about is like a rainforesty kind of. Oh, you know what? Speaking of like the star sizes themselves, I didn't even
Hmm.
know that a smaller star is more stable.
Yeah. Uh, there's not as I'm hesitant to say there's not as much solar activity because I think that just the solar activity is different at smaller sizes. The amount of pressure. So the star exists in a state of equilibrium between two competing forces. It's the gravity pulling everything in, and the radiation pressure from fusion, at its core, pushing out. And when you have a smaller star, you have less gravity pushing in, so there's less rate of fusion in the center. If I believe I'm correct about that, which means that because things are burning at a slower rate, you have much longer longevity and much more time for stars or for life to form on planets that are surrounding the star.
So when you said that planets, their rotation also matters, were you talking specifically, or maybe it's both, about the planet spin itself or its orbit around the star? Does that also come into equation?
So the planet being closer to the star will mean that the time that it takes for it to orbit the star should be faster as well.
Oh, okay. Didn't even know
Um,
that.
yeah, you can kind of think about it like
A drain?
yeah, or I was gonna say like a ballerina when they have their arms out. You can kind of think of like if
Oh.
the planets are out at the farthest distance, they're kind of going slower. If you move further in, you go faster.
Yeah, it's like a
Um,
tire swing.
yeah, yeah. And so when you have planets that are much closer in, say the same mass as Earth, they're gonna have to go a lot faster to maintain that orbit.
Oh, okay. So as we get closer to the sun, will our years go faster? Because the Earth will spin quicker.
Yeah, so as if we're not getting so much closer to the sun that it should be an issue, but it might mean that 1 year, our leap year wouldn't exist anymore,
Oh man,
the like extra day.
we're gonna
But
lose time.
just in how we measure it, um,
That's true. Everything will change and everything will update automatically, or someone will already have a bug fix or something.
but that shouldn't happen for billions, I believe. Yeah. Another aspect of this stability, when a star starts to die, there's a lot of volatility to the star. Usually, well, depending on the size, it can puff up and increase the radius of that star, which for our sun would engulf us eventually. Um,
That
uh,
much. Holy
yeah,
crap.
yeah. So having as much time, I mean, this is in 5 billion years for us, but having as much time as possible before you get to those end of life stages will allow us to develop life.
Somewhere else?
Oh, but yeah, or just on the planet surrounding before they die.
Yeah, I got you.
Um,
We gotta get the hell out of here. We
yeah.
only got 5 billion years. We
Well,
better find some water or make some.
we of the stars thought to be suitable for life, there a conservative estimate says about 2% of those stars have planets that are in the habitable zone. And there's these types of stars are the most abundant in the universe. So we have a good chance of finding another planet in the habitable zone that we could possibly venture towards
Yeah, I
in
guess we
four
shouldn't
billion
rely on
years.
Mars then.
Yeah.
Why did we move all our real estate to Mars if the Earth is just gonna die anyway?
And depending on the model that you're looking at, it'll also subsume Mars.
Now, I wonder if there's can there be a planet where it's rotating around a smaller sun, but the planet itself is larger with water?
Yeah, yeah. Actually, a good example of this, which I was gonna, it's a good example in a lot of different ways, is Kepler 22b. It was the first exoplanet discovered in a habitable zone around an Earth-like star. Sorry, or a sun-like star, where liquid water could exist on the surface. It is 2 times the radius of Earth, and 9 times the mass of Earth. It is slightly closer in. It's a orbital period of 290 days instead of our 365, and it is about 80% away from its star as we are. So if we're like 100%, it's 80%.
We got to get a freaking ship out there.
It is about I can't remember exactly, but I think it was like a 160 light years away.
And because I'm just a plebeian. And for anyone who might be listening who doesn't know, because I sure as heck don't, what is an exoplanet? An exoplanet.
An exoplanet is a planet that's orbiting around a star other than our own.
Oh, that's all.
Yeah.
That's easy. I got that. Got it.
uh, just to denote, differences instead of just saying planet, planet all over.
Yeah,
to
no, that makes sense. Not in our neighborhood.
Not in our neighborhood. Yeah. Um, yeah, this Kepler 22b, the exoplanet, is it's been dubbed a water world
Heck yeah,
because
I've also seen that movie.
I actually haven't, but there is expected to be an ocean covering the majority of its surface.
Now, could that what's because we have fresh and salt water. Is there a
Hmm.
way to maybe determine like what kind of if it would have salinity or if it would have like some other I don't know iron or mineral in it or something like that?
Yeah, so the best way to do that would to kind of figure out what elements are in its atmosphere. We would expect it would have a similar cycle to that of Earth of water evaporating and turning into clouds and then coming down. And so whatever the salinity of the water would be in the atmosphere as well. I can go into how we can detect that in our atmosphere. It takes a just do a few steps back for how we detect the exoplanets in general first, though.
Sure, sure.
Okay, so the majority of exoplanets are detected using something called the transit method. This is where you have a star that you're looking at, and there's a planet that's orbiting that star, and it passes in between the star and us. And so for a very short period of time, that star is dimmed by the planet passing in front of it. And it could be an hour, it could be 10 hours. And the dimming that we see is a few like parts per thousand dimming, um, about less than 1% sometimes for something like Earth. For something like a Jupiter sized planet, that's about 1% dimming, I believe.
And you had mentioned in the pre-show something along the lines of spectroscopy. Is that what does that have to do with
Yes.
exoplanets?
So when we are looking at this planet transit, we can see how light that we see changes as this planet goes across the sun. And so spectroscopy is uh, we are looking at the light's kind of signature in a sense, in a looking at it in all the different frequency bands. And so looking at like red, green, blue, all and into infrared and X-ray. And each element kind of has like a barcode to it that it absorbs and emits. And when light goes through a planet's atmosphere to us, it would absorb certain lines of frequency lines depending on the composition of that atmosphere. And so you'd get a unique barcode for each atmosphere of a planet.
Wow, and we
And
can we can do this stuff. That's crazy.
yeah, yeah, we
That's
can do
crazy
this.
cool.
I currently the JWST, the James Webb Space Telescope, is the most sensitive tool we have to do this in space.
And
Um,
someone's just sitting there with a barcode scanner going beep beep, logged
yeah,
it.
a lot of fitting different models to see, is it this element or is it that element, and all of that.
That's really cool. I'm learning so much right now. And let's talk a little bit about moons because I know some moons with planets can also perhaps hold water.
Yes, we have two really good examples in our solar system. One around Jupiter and the other around Saturn. So the first one around Jupiter is called Europa. It's one of the Galilean moons. It's the second closest to Jupiter. It's very smooth, icy exterior with ocean underneath. It's actually only slightly smaller than our moon, and it's the smoothest object we have in our solar system. And it's smooth because of the ocean underneath. And there's this tidal heating. Each of these Galilean moons are in resonance with each other. And so they orbit at different kind of like harmonics of each other. I don't remember the exact frequency. I think it's 2 to 1 for Europa and Io, which is the closer moon. And every time that Europa goes around Jupiter, Io has gone around twice.
That's that's fast.
It is. Oh, I mean, Europa's a little further out, so it has more distance to travel. But other moons also have a similar frequency, and it causes this tidal heating and deformation.
Oh, so
By
it's
this,
it'd be choppy.
um, well, it actually is really, really smooth on the surface because these ice plates on top move similarly to tectonic plates. And whenever they move, the water that's exposed underneath just fills in
Oh,
and creating this very, very smooth surface.
okay.
Hubble has even observed these like plumes or geysers occur during any of these tectonic activity.
So it's like water just whoosh right up and then gone.
And then, yeah, and just kind of fills in the ice with ice
Ice with
like that.
ice.
Yeah,
So it's not. It's kind of similar to our tides, a little, or no?
in a sense. Yeah,
Okay.
yeah,
And we have tides, but there's also tidal friction, and that's kind of what you're talking about.
yeah. So, um, if we're thinking about our tides, they're kind of influenced by two things: the sun and our moon. The water is kind of bent and stretched, like it's. If we think of Earth as a circle, the water is kind of an oval around it. And if you have the like longer parts of the oval, the moon is on one end, kind of driving that force.
I knew that one. I knew that.
Yeah. And so it's a similar thing that's happening for Europa, except it's not just Jupiter and the Sun. It's Jupiter and Io and Ganymede and other moons of Jupiter that are having this tidal force on it.
So then, when you said that this moon that would be covered in ice, kind of like tectonic plates, would that be considered an all ice planet, or no? Because there's still water underneath that.
It wouldn't. There's still water underneath it, so it wouldn't be an all ice planet. Yeah, that actually it reminded me of the salinity you were mentioning before. There is, I believe, for there to be some like convection occurring because they measured some salinity, like uh some I'm trying to remember the words that were used when I was reading this. There's a little bit of essentially like the bottom of their sea that they could see come out of the geyser.
Oh, okay. So they're trying to measure what's in that.
Mm-hmm. Mm-hmm.
Okay, okay. To see whether or not it would freeze more, or just for the composition, I guess.
Yeah, and if you're seeing some seafloor come out at the top, it means that there's continued motion of the water, which is the cold water at the top is being brought down. It sinks down a higher density than the heat rises, cool falls.
Could that also be indicative of maybe, well, I guess they wouldn't see it if there was ice, but volcanic activity under the water to push?
There might be, yeah. Which is all really good signs for finding life.
Yeah, yeah, because especially here on Earth and the ocean, I know for a fact that the volcanic activity under the water is a breeding ground for life,
hmm hmm
which is really cool too. I don't know if you've ever scuba dove or anything like that. I highly recommend it because
No.
it is beautiful.
Okay. Add it to my list of things to try out.
At least once, at least once.
Yeah.
Just it's pretty cheap. You can get it on Amazon, probably $20 a mask and snorkel.
Okay.
And yeah, snorkeling, and if you can't go scuba diving, but snorkeling's fantastic too. Okay, so let's pretend we're now in a habitable zone. We've got the perfect star size, the perfect planet size. We're spinning all good. We're I don't know, we're around the same size as Earth, or we're the what we need to be to essentially have some life on this planet, to get some freaking water going, you know?
hmm
Do you consider water the building block for life? If there's water, you think there's a pretty good chance we'll find something living?
So, in terms of water being if there's water, do we have a good chance of finding something living? I think yes. Uh, if it's at that moment that we're checking, maybe not. Maybe give it a few hundreds of thousands, maybe a few million years. But yes, I think if there's liquid water, there will be life at some point. Is water the building block for life? I think yes and no. No, water is not essential to life. Life could have evolved needing some other base compound. But I think water is, as we talked about earlier, water is very abundant. So it's more likely than not that water was involved in some way for life to form. Water is also a really good solvent. It dissolves things really well. It's non-reactive. And as we talked about earlier, its solid form floats on top of its liquid form. So it protects life from extreme temperatures. And right now, we don't know of any other solvents that have these properties. So it's very good for supporting life.
It's the rock star of the chemical world for needing a good start then.
Yeah. Yeah.
So it's not a sure guarantee for life, but
Mhm.
it is much more likely.
Yeah. I mean, we had water on Earth for millions of years without life. So something changed.
Yeah, who knows really what the perfect timing is that something will change over, I guess. We don't truly know.
Yeah.
We just got lucky.
That we did.
Now we got cars and iPhones. So then let's talk again about the ice caps on Mars. Since
hmm
Mars has ice, do you think if we gave Mars enough time that the ice caps could ever melt and form some sort of atmosphere and life there?
So I don't know. I think eventually, when our star becomes a red giant, it'll heat up a little bit on Mars. But uh, if Mars has enough of because it's not just water, it's also protection from radiation. A certain amount of radiation we think is necessary for life or starting life, but having too much kills it as well. So the fact that Mars has a very weak atmosphere, that's not going to change by Mars heating up.
And you said the most abundant most abundant compounds are what? Carbon and something else?
Carbon monoxide,
Carbon
CO.
monoxide. And what are the top? Do you know like the top three other than carbon monoxide?
Um, I think it was carbon monoxide, uh, and then water and something else were like tied for second, and I can't remember what the something else was.
Okay, because I was always wondering, like, if there was some sort of like desolate planet, would there be a way for us to maybe pull those compounds out of other things to create water somehow as a resource to get it on a planet instead of transferring it from somewhere else or something like that.
Hmm.
That's just like a sci-fi kind of thought, I guess. I have no idea. I'm just talking about it.
Yeah, I mean, I think it's definitely possible. It depends on what kind of compounds exist in a different planet's minerals and atmosphere and what we can use to harness that.
Yeah, that sounds like you know what you're talking about. uh, did you happen to watch the what was it? Oh my gosh. Matt Damon, the Martian, the Martian Man,
Yeah,
or is that what it was? The movie
The
called
Martian.
The
Yeah,
Martian? Yeah,
by the book was by Andy Weir.
yeah. The did you watch the movie too?
I did. I did.
Did you enjoy it? I thought it was pretty good.
Yeah, I did enjoy it. Space movie where everyone ends up okay.
Yeah, it was cool. The ending. I don't want to. I guess I won't say any spoilers, but I'm
Yeah.
forgetting because I know he grew potatoes, but I couldn't remember how he got the water. If it's from water he had.
I think some of it was water that he had. There's a filtration system that they have to like reuse from pee.
Oh, okay. Actually, yes. I think I remember that. I think I remember
And
that.
then I think he grew it with fertilizer from his poop.
Yeah, poor man's fertilizer.
Yeah.
Hey, he had to do what he had to do, and he got through it.
Hey, yeah.
All right, Alex. This has been freaking awesome. I've learned so much tonight, and I really appreciate you coming on here. Is there anything else you'd like to talk about with us today?
No, I think we covered everything I had to say.
Awesome. Well, like I
Thank you.
said, thank you so much for coming on here and sharing your intellect with us. I hope you get through the rest of your studies easy. You get that PhD. You
Thank you.
feel great walking off that or I guess you I don't know if you're going to walk off for your PhD, like walk off a stage or anything, but if you
Uh,
do,
okay.
power to you.
Thank you.
I don't know how a PhD works. I'm not a I'm not a doctor,
Uh,
but I wish you nothing but success.
Thank you. Thank you. This was very fun to chat with you.
Thank you, thank you. I appreciate that. Maybe sometime in the future, if we come across more discoveries, we can bring you back on after you've got your PhD.
All right. I'd be happy to do so.
Yeah, I would love to talk again. Okay, Alex, thank you so much again. And that will be all for tonight, folks. This has been All to Do with the Blue. I'm your host, Rowan Whites. And if you would like to share a story about the Blue with us, I can get you on the show. Just email me, send me a little chit chat story. We can get you on here. Thanks, everybody. Have a great night, Alex. And have a great night to you all.